So this video is going to go over applied derivatives and the physics applications of derivative calculus in AP Physics C mechanics problems. These are primarily going to be the sorts of problems where you need to use a derivative to find the answer and you've got actual numbers. So first, a little review. When are derivatives used in Physics C? A lot of the times you're going to be finding velocity and acceleration graphs with a position function, or you'll be finding the acceleration from the velocity function. Additionally, you could find force from the potential energy within a system, and using derivatives, you can find force applied using the momentum of an object over time. In addition to the general derivative rules listed, you're going to be using primarily the power rule when it comes to derivatives, as usually in Physics C, the sorts of derivatives you're going to be taking are pretty basic, and it's more about the concept rather than being able to take difficult derivatives. So first, on position, velocity, and acceleration. X of t will often notate a position function where the base unit's going to be in meters. V of t, or velocity over time, the velocity function, will have a base unit of meters per second, and a of t, the acceleration function, will have a base unit of meters per second squared. These functions can be achieved when given another function. For example, when given the position function, you can achieve the velocity or the acceleration function with the use of derivatives. As you can see in this slide, the position function, often notated by a certain function over time, can get you the velocity function by taking the first derivative of the position function over time. And the acceleration function can be found by taking either the first derivative of the velocity function over time or the second derivative of the position function over time. Now on to potential energy and force. The potential energy is sometimes given with a graph or an equation, and to find the force being applied to an object, the derivative of the potential energy function will result in a force function over time. This also applies to graphs, as the slope of a graph will be the negative force applied. You can see here the potential energy and force functions, as a force function will result from the negative potential energy over distance function. And finally, with momentum and force, as when given a momentum equation, the force can be found by taking the derivative of the momentum over time. And because the average force on a constant mass system is equal to the rate of change of the momentum. So now we can look at some practice questions. So first, question 2 in the packet. The question says the speed v of an automobile moving on a straight road is given in meters per second as a function of time t in seconds by the following equation. V of t equals 4 plus 2t to the third. And it asks, what is the acceleration of the automobile at t equals 2 seconds? So the question is asking for the acceleration of the automobile, and we are given the velocity function for the automobile. So as I said earlier, the acceleration function can be found by taking the first derivative of the velocity function, and by doing that, using the power rule, you get that the velocity function is equal to 6t to the second. Now, using that velocity function, you can plug in a t equal to 2 to get the acceleration at 2 seconds. And when you do plug that in, you get 24 meters per second squared. So a similar question is number 4 in the packet, where the velocity of a particle moving along the x-axis is given as a function of time by the expression v of t equals 3 times t to the second minus 2 times t plus 4, where v is in meters per second and t is in seconds. It asks, what is the acceleration of the particle at t equals 2 seconds? Similarly to the first one, we're given a velocity equation and asked to find the acceleration of the particle at a given time. So the first thing you're going to do is take the first derivative of the velocity equation. Using the power rule, you get that v of t, or v prime of t, or a of t, is equal to 6t minus 2. And subbing in 2 for our t value, you get 6 times 2 minus 2, which is equal to 10 meters per second squared. So then on to question 6 in the packet. It says an object is moving along the x-axis, which position x is given as a function of time t, defined by the equation x of t equals 2t to the third minus 3t to the second minus 8t minus 3. Which of the following equations indicates how to determine the object's velocity v as a function of t? Now, similarly to the previous problems, you're going to be taking the derivative of the position function to find the velocity function, as the first derivative of a position function over time will give us the velocity function over time. And as you can see, the answer is v of t equals the derivative of the velocity function, of the position function. So now we can look at question 13 in the packet, which tells us the momentum of p of a moving object is a function of time t, where the given expression is p equals kt to the third, where k is a constant. It asks what the force causing the motion is, and as we know the force is the derivative of a momentum over time equation, we can simply take the derivative to get 3kt to the second, which is equal to the force. So then for number 14, this is a potential energy equation. It says if the potential energy function is given by u sub r, or u of r equals br to the negative 3 over 2 plus c, where b and c are constants, which of the following is an expression for the force on the particle? Now, because b and c are constants, we can simply take the derivative of the potential energy equation to get force, and that will give us a derivative or a force equal to 3b over 2 to r times r to the negative 5 halves. So question 15 in the packet tells us the potential energy U as a function of the position x of an object is given by the equation U of x equals negative 400 over x, where U is in joules and x is in meters. The object is released from rest at position x equals 30 meters and is free to move along the x-axis. When the object has moved a distance of 10 meters from its initial position, the magnitude of the force associated with the potential function energy is, and as you can see, we take the derivative of the equation as the derivative of the change in energy over distance is equal to the force. And in doing that and plugging it in for 10 meters, we get the force at 10 is equal to 400 over 10 squared, or 4 newtons.